This is Chapter 4, Differential Relations for Fluid Flow, Part 5. In this video, I'm going to go over two exact solutions to the continuity and Navier-Stokes equations. The first one is laminar flow between fixed parallel plates, and this is called Poiseuille flow after a French physicist from the 19th century. And then we'll look at a situation where it's still flow between parallel plates, but the upper plate is moving. It's moving at velocity v, and the lower plate is fixed. And this is called Couette flow after another French physicist. So starting with the situation where we have two parallel plates, here's the problem definition. Consider steady laminar, incompressible, viscous flow between fixed parallel plates, and you should notice that they're located at distance 2h apart. So this distance here is h. The plates are considered to be very wide into the page and very long, so the flow is purely axial. So we have that the y and z components of velocity are 0. And we're told to neglect here gravity effects. Now, that's not absolutely necessary. If you leave gravity in, acting in, say, the negative y direction, it just adds a hydrostatic pressure gradient. So there's really no big deal, but it makes the solution a little simpler if we just ignore gravity. It doesn't change the velocity field. So we start with the continuity equation in incompressible form. Di u di x plus di v di y plus di w di z equals 0. Now we can cross out some terms here because we know that v is 0 everywhere and w is 0 everywhere, so there's no spatial variation in those variables. And so you just end up with di u di x equals 0. What that says is that the rate of change of u in the x direction is 0, so u is not changing as the flow moves downstream in the x direction. This type of flow is called fully developed flow. And what it means is you're far enough away from wherever this flow entered between the plates such that no flow entrance effects remain. Now, as a complete side comment, I just thought at this point I would talk about developing flow. What happens if you are near the entrance? Because the flow has to come into those parallel plates at some point. And what happens is, and I've shown an image here down below, is that the flow enters and it has quite a uniform velocity profile, and then boundary layers grow on the walls because of the no-slip condition and the viscous drag of the fluid. The fluid near the wall is slowed down by viscous effects, and you get these growing boundary layers where viscosity has slowed the fluid, and eventually the boundary layer off the upper plate and the boundary layer off the lower plate merge, and you get this parabolic flow. Of course, we haven't shown it's parabolic yet, but we will when we do the analytical solution. So the boundary layers merge, and then from that point on, shortly after the boundary layers merge, the velocity profile does not change anymore, and you have this fully developed flow where di u di x is 0. And the current exact solution is for exactly that case where we have fully developed flow. So let's go back to our problem now. That was a complete side comment about developing flow. So we have fully developed flow. We've just shown that by looking at the incompressible continuity equation. So now we can move on. So we have 1D flow, and we can write the Navier-Stokes equation in the x direction. So this is conservation of momentum in the x direction. And you can see we have the acceleration terms here. We have the local acceleration, the convective acceleration, the pressure term, the viscous terms, and the gravity term. But we know that some of these terms are 0, and so we can do a little simplification. So let's go through these simplifications in some detail. We're told in the problem statement that the flow is steady, so du dt, any derivative with respect to time is going to be 0. The local acceleration is 0. We showed using the continuity equation that the flow is fully developed, so du dx is 0, so this term, this convective acceleration term is going to go to 0. We have one-dimensional flow. There's no y component of velocity, so this convective term goes to 0. And similarly, there's no flow in the z direction, so there's no convective acceleration in the z direction either. We just showed that the flow was fully developed, so the flow is not changing. The u component of velocity is not changing in the x direction, so the second derivative is going to be 0 as well. There's absolutely no flow in the z direction, so there's no variation of u in the z direction. And we're told in the problem to neglect gravity. So you'll notice now that all the nonlinear convective terms are 0, and in fact that's what makes the analytical solution possible in this case. Also, I just want to point out that since the y component of velocity, and w, the z component of velocity, and gravity is neglected, if you write down the Navier-Stokes in the y and z directions, you'll cross out all the terms except for the pressure gradient terms, and so you can easily show, I'm not going to do it here, that the dy and dz is 0. So we get that the result is that the pressure is only a function of x. So now we can simplify this whole thing. The only terms that remain are the viscous term, the mu du dy term, and we have the pressure gradient term. And so you can simplify this. Note now that I've put this in full derivatives because u is only a function of y and p is only a function of x. So we have converted our partial differential equation into an ordinary differential equation. I'll talk on the next slide about why this is equal to a constant. So why is this the case? Well, there's a couple of arguments for why this equals a constant, this expression equals a constant, and I would remind you of your differential equations course where you used the method of separation of variables, probably to solve Laplace's equation. And what we have here, we have two equal quantities. We have p, a function of p and a function of u, and one of them only varies in the x direction. P is only a function of x, and u is only a function of y. And the only way this can be true is if they equal a constant. Otherwise, they would be independent of each other and they couldn't be equal. So that's a mathematical argument for why they have to equal a constant. There's also a physical argument to reach this same conclusion. Think about what this pressure gradient dp dx is. It's caused by the drag on the wall of the fluid, and I've shown here the viscous drag here and here. We did an example of this back in a previous chapter, right? That the drag at the wall is du dy evaluated at the wall, and I've shown the arrows. That's the drag force on the fluid. And the pressure gradient is the pressure in the x direction, pressure gradient in the x direction necessary to drive the fluid to overcome that fluid friction. Now we know that velocity profile, the u velocity profile, is not changing in the x direction, so these shear stresses would not be changing in the x direction either. So we could argue that the pressure gradient required to overcome that fluid friction is also a constant. So that's a physical argument. The pressure gradient doesn't change with x because the velocity gradient doesn't change with x, which means that the shear stress at the wall doesn't change with x. I should point out that this constant is a negative value because dp dx, pressure is going to be decreasing in the x direction because of the viscous shear. So we expect dp dx, while it will be negative, to drive the flow in the positive x direction. So we have mu d squared u by dy squared equals dp dx equals this negative constant. we can now perform some integration. So integrating once with respect to y, treating dp dx as a constant, of course. Here we just get, and I brought the mu over, 1 over mu dp dx y plus c1. We can use the fact that we have flow symmetry about the center line, about y equals 0, to evaluate c1. The book doesn't do it this way, but it's a really nice way to do it. We have no slope here, so we have du dy at y equals 0. Our axes are on the center line here. y0 is on the center line, equals 0. So if we apply this symmetry, we can set, if we substitute in here the center line 0, we know that this is 0, and we get, therefore, that c1 is 0. So we can cross out c1. Now we have just this expression with c1 gone. So we have du dy equals 1 over mu dp dx, where dp dx is a negative constant, times y. So we can integrate again with respect to y, and of course that's going to become y squared and divided by 2, and we get another constant. Now this time we can evaluate this constant here, c2, by considering the boundary conditions on either the upper or lower wall. It doesn't really matter, as it turns out, because we have y squared. So at y equals plus or minus h, we have the no-slip condition, right? We have the no-slip condition here and here. So the velocity goes to 0. And so if we put in here 0 and y equals either plus or minus h, you get that c2 equals minus 1/2 1 over mu dp dx h squared. So now we can make the substitution in here for c2. I think I do that on the next slide. Okay, I've written down, here's our general expression with c2. We've just shown that c2 equals 1 over 2 mu dp dx h squared. So now I'm going to make this substitution here and do a little bit of simplification. So making the substitution, and you can check my math, I've pulled out h squared, so you get minus h squared over 2 mu dp dx, which is a negative constant, 1 minus y squared upon h squared. And so you can see if you put y equals 0, which is where the maximum velocity is, if you put 0 in here, you get that the maximum velocity is minus h squared 2 mu dp dx. Now, I have emphasized that the pressure gradient's negative, so it looks funny that the maximum velocity has a negative sign here, but in any real flow, dp dx is going to be a negative number, so you'll get a positive value for the maximum velocity. And so you can simplify this and just write it as u over u max, and you get this parabolic velocity profile. So the velocity profile for laminar flow between parallel plates is parabolic, is called Poiseuille Flow, after a French physicist, and this result was published around 1840. Now we have the velocity profile. We can integrate this to get the flow rate, because that's what's often useful. So our flow rate is the integral from minus h to plus h of u dy, velocity times area. Our incremental area is dy, times unit depth, of course. And so I've just made the substitution in here for u and performed the simple integration. So this is going to become y cubed upon 3, and then you evaluate it at the two limits, minus h to plus h. You can check my algebra here. I'm quite confident it's correct. And you get minus 2h cubed upon 3 mu dp dx, where dp dx is this negative constant. Now if you check this out, if you substitute in, we just showed that the maximum velocity was minus h squared over 2 mu dp dx. If you make that substitution into here, you get that the flow rate is 2/3 the maximum times 2h. Now I've put 2h here because that's the full cross-section here. This cross-section is 2h. And so now we have our flow rate in terms of our maximum velocity, and that's got to equal, of course, the average velocity times the total cross-section, 2h times, of course, we're assuming unit depth here. And that gives that the maximum velocity is 1.5 times the average. That's an interesting result, that the maximum is 1.5 times the average, and I've shown it here. There's the average velocity versus the maximum. Be careful, this is a slightly different result than for a round pipe. For a round pipe, because the incremental area here, we wouldn't use dy, we'd use 2 pi r dr. The integral works out slightly differently. And I think we discussed this earlier, that for a round pipe, the maximum is actually 2 times the average. So be careful. Laminar flow in a round pipe and laminar flow between plates, both of them have parabolic velocity profiles, but the relationship between the maximum and the average velocity are different. So that completes, I think, the discussion of flow between fixed plates. We now move on to discussing flow between parallel plates where the upper plate is moving. So this is this Couette flow. So I'm going to do the problem definition again the same way. So we're considering laminar, steady, incompressible, viscous flow between two plates. This time the total distance is h. So that distance is h, not 2h, as we did in the previous example. And in this case, flow is driven by the upper plate moving at velocity v. So we don't have a pressure gradient this time. We don't have a pump driving the flow between these plates. It's actually the viscous drag of that upper plate that's dragging the flow along the channel. Again, we're going to assume that the plates are very long and wide, so the flow is purely axial. We have no y component, no z component of velocity, and we're going to neglect gravity effects. Not that that's necessary, but if you added gravity in, it would just add a hydrostatic pressure gradient. It wouldn't change the flow field. It just makes our life simpler to neglect gravity at this point. So we start again with the incompressible three-dimensional continuity equation. We can make the same arguments here, that there's no v component, there's no w component, so there's no variation in the y or z direction, and you get that the flow is fully developed. We have one-dimensional flow. We can write the Navier-Stokes in the x direction. I'm going quickly over this because we went over it in some substantial detail last time. We have exactly the same Navier-Stokes equation. We can get rid of the steady term, fully developed. It's a one-dimensional flow, so v and w is 0. But in this case now, we don't have a pressure gradient. It's the viscosity of the fluid and the movement of the upper plate that's driving the flow. So our pressure gradient term goes to 0. Similarly, the di squared u by dx squared term, it's fully developed, so there's no variation in the x direction anymore of u, and there's no variation of u in the z direction. And we're neglecting gravity. So again, the nonlinear terms are 0, and we can simplify this. The only term that remains is di squared u by di y squared. And again, you'll notice I've changed the partial derivative to full derivative now because u is only a function of y, so we've converted our partial differential equation into an ordinary differential equation. So we have just that d squared u by dy squared equals 0. Very easy to integrate. We integrate once, we get a constant c1, we integrate twice, and we get a constant c2. So you can see it's a linear profile, and we'll evaluate c1 and c2 using the boundary conditions. So we've got these boundary conditions, the no slip. So at y equals 0, we have that the velocity is 0, and at y equals h, we have that the velocity is equal to the upper plate, capital V. And so very simple here, we can apply these boundary conditions. Applying the lower one, the fixed surface, we get 0 equals c1, 0 plus c2. That shows that c2 is 0. And then we put in this expression for y, we put in h, and we set u equal to our capital V, and we get that c1 equals v over h. So the result is you end up with this linear profile where the u component of velocity is just the upper plate velocity, and then it varies linearly proportional to the distance from the plate, so y upon h. So if you put y equals 0, you recover the no-slip condition. If you put y equals h, you recover the velocity. And it's just a linear velocity profile. You may recall that in Chapter 1 we made this assumption when we were doing viscous stress calculations on plates. And we made that assumption without proof. So now you've seen the proof. Laminar flow between parallel plates with flow driven by motion of the upper plate is linear, and it's called Couette flow. Again, after another French physicist from the 19th century, 19th and 20th century. And that completes this video.